In section 6.5, we're going to be working on solving special types of linear systems. And one of our learning objectives for this section, our primary learning objective for this section, is to identify the number of solutions in a linear system. And I discussed this a little bit in the introduction to 6.1, but mostly we've been focused on, so far in the rest of the chapter, with consistent linear systems which all have one individual solution. So a single point as a solution. So we've been working with consistent independent systems. And in this section, we're going to be working on inconsistent systems and consistent dependent systems. Again, we're so focused on systems of linear equations, and we want to remember what parallel lines are like. So when you think about the number of solutions that we have in a linear system, remember we have basically three different scenarios. We've got two lines which will have a single solution. We can have parallel lines which have no solution because they don't intersect. And then we have lines that are actually equivalent equations and they're the same line, which have an infinite number of solutions. Those are the three different types of systems that we work with. So when it has one solution, it's a consistent independent system. When it's parallel and there's no solution, it's called an inconsistent system. And when it has an infinite number of solutions because they're actually two equations that create the same line, that's called a consistent dependent system. So the way I would know a system with no solution is there are two different ways I might identify it. I can tell by putting into slope-intercept form, and I'm going to have the same slope for my two lines, but different y-intercepts. So that's one way to go about it. I'm going to do that way first. By adding y and adding 4, I'll get x plus 4 is equal to y. So I have a slope of 1 and a y-intercept of 4. And over here I'm going to add 3x and I'm going to divide by 3. And I'll get y is equal to x plus 2/3. I have a slope of 1 again and a different y-intercept, a slope of 2/3. So by noticing that and I'm going to go ahead and put the 1s in here for the slope. By noticing that my slopes are the same, but my y-intercepts are different, I can tell that these are parallel lines. They will never intersect. They will never have a solution. If I work on it algebraically by using one of our other methods, what happens is the variables will drop out, and I will be left with an untrue statement. So let me go ahead and do this with substitution. So if I solve for x, I'll get x is equal to y minus 4. And if I plug that in place of x in the other equation, negative 3 times y minus 4 plus 3y is equal to 2. So I'll get negative 3y plus 12 plus 3y is equal to 2. And the y's drop out and I get 12 is equal to 2. Well, that's not true. That's how I know that I've gotten an untrue statement. My variables have all dropped out and I have an untrue statement. That's a sign of an inconsistent system. Okay, if I did this with combination, I might take this first equation and multiply it by 3. I'll get 3x minus 3y equals negative 12. And I have negative 3x plus 3y is equal to 2. And when I add together, I'll get 0 is equal to 10, also untrue. Okay, so it didn't matter how I did this. If I graphed it, I would have gotten parallel lines. I did substitution and I got an untrue statement. I did combination and I got an untrue statement. Those are the signs of an inconsistent system. Okay, this is going to be the sign of a consistent dependent system, right? Infinitely many solutions. What's that going to look like? If I put it into slope-intercept form, it's going to have the same slope and the same y-intercept. They'll be the same equation when I put them into slope-intercept form. So over here, if I subtract x from either side and divide by 3, on the first equation, I'll get negative 1/3 x minus 1/3. And over here, I'm going to add 6y to either side. I'm going to subtract 2, and I'm going to divide by 6. Maybe that's too many steps all at one time. So let me just subtract 2 and add 6y. And then I'll divide by 6, and when I get it over here, I'll get negative 2 divided by 6 is negative 1/3. And 2 divided by 6 is also 1/3. And you see, when I put them in slope-intercept form, I have the same equation. So that's one way to do it. Another way to do it would be to do substitution. So if x is equal to negative 3y minus 1, then I can plug that into the other equation in place of x. So I'll have negative 2 times negative 3y minus 1 minus 6y equals 2. So I'll have negative 2 times negative 3y, that's going to be 6y. Negative 2 times negative 1, that's going to be plus 2. Minus 6y equals 2. And I get 2 is equal to 2. So in this situation, all of my variables again dropped out, but I'm left with a true statement. That means I have an infinite number of solutions. That's what this looks like. If I did it with combination, I could take the top equation and multiply it by 2. And I don't need to change the other equation. And when I add everything together, I'll get 0 plus 0 equals 0. That also is a completely true statement, a sign that I have an infinite number of solutions. Okay, let's take a look at the idea here about, from the book, is exactly what I've just described to you. If there's one solution, my two equations have different slopes. If there's no solution, same slope, different y-intercepts. Infinitely many solutions, same slope, same y-intercept. Okay, so I'm going to add y and add 9 to either side of this equation. And on this one, I'm going to subtract 3y and divide by 5. All right? Or sorry, I'm going to subtract 3x and divide by 5. So in this case, y will be equal to negative 3/5 x minus 3. Different slopes, right? We have a slope of 3 and a slope of negative 3/5. This has got one solution. If we take a look at this one, right, I'm going to add 3x and divide by 4. So y will be equal to 3/4 x plus 3. I'm going to do the same thing here. I'm going to add 3x and divide by 4. Y is equal to 3/4 x plus 6. So I have the same slope, but I have different y-intercepts. Okay, these are parallel lines. This has no solution. Okay, and I've already shown you what it looks like when I have the same equation. These become the exact same, or sorry, infinitely many solutions. These both become exactly the same equation. Looking at this in context, I have one admission to a roller skating rink costs $X. and renting a pair of skates costs Y dollars. If a group pays $243 for admission for 36 people and 21 skate rentals, another group pays $81 for 12 and 7 skate rentals, is there enough information? So my admission, right, is 36 people would be 36x, and then the skate rentals would be 21y, and the total price for that group is $243. In the other group, 81 for admission for 12 people, so $81, a mistake, is what they paid. Admission for 12 people and 7 skate rentals. So I could see that if I multiply the bottom equation by 3 and subtract, I can get rid of either the y or the x. That's a hint to me that maybe this is a problem, right? So 36x plus 21y equals 243, and 36x plus 21y equals 3 times 81 is also 243. I get 0 equals 0. So there's not enough information. What I get is there's an infinite number of solutions for this x and y. These two are modeling an identical situation essentially. So I cannot solve this. So not enough information is the answer. Any price that I chose would work because of the ratio of admissions to skate rentals is the same in both of these equations. That's essentially the problem, but this becomes not enough information. Okay, so again, this is a reminder of something I've stated now in this chapter 3 times. Two lines with different slopes intersect in a single point, you have one solution. Parallel lines don't intersect at all. That has no solution. And when you actually have equivalent equations, they create the same line. Every point on each line is a solution, so there's an infinite number of solutions.